In this video, we're going to talk about the circuit element known as a capacitor. This is our typical symbol for a capacitor, right? We just have these two parallel lines. Sometimes you will also see capacitors where one of the lines may be curved, something like that. But regardless, we'll pretty much use the two straight lines in any of our videos here. And the thing is, with a capacitor, it is different than a resistor. For a resistor, you have a simple formula, V equals IR, Ohm's law. But that rule no longer works for a capacitor. In fact, you need calculus in order to relate the voltage and the current. And there's two ways you can write that. You can write that down as the current is equal to the capacitance times the derivative of the voltage. That's kind of similar to the V equals IR. Or the other way is if you were to kind of solve that equation for voltage, you see that the voltage at any given time is equal to the voltage at whatever starting time you have plus 1 over C times the integral from the starting time to the current time of the current. And again, that's really just integrating here both sides from T0 to T, and you'll get that formula right there. So in order to relate voltage and current for a capacitor, algebra is no longer sufficient. We need to use calculus to do so. Now there are two important properties of a capacitor that, again, a resistor does not have. The first is that the voltage across a capacitor cannot change instantaneously. So the idea here is that if you had a resistor and you applied 5 volts to it, and then immediately you flip the wires and now you're applying negative 5 volts, you can do that with no problem across a resistor, and it's just going to flip-flop the current when you do so. However, for capacitor, this is not possible. And one of the reasons why you could say that is the current is supposed to be the derivative of the voltage, but there is no derivative here. The derivative would be undefined, and so that would not make any sense physically, and that shows you that the voltage across a capacitor cannot change instantaneously. I will say, however, that the current across a capacitor can change instantaneously, and the voltage can change very quickly. Like maybe the voltage will change over a time period of a couple hundred milliseconds. That's certainly possible, but it cannot change instantaneously. So you're not going to have any of this discontinuity type stuff happening for a capacitor voltage. The second thing here is that under steady state with a DC source, a capacitor acts as an open circuit. So what that means is if you have a circuit with a typical DC battery and you have your capacitor in there, as you plug in your battery, current's going to start flowing and it's going to charge up the capacitor here more and more and more. At some point in time, the capacitor is going to become fully charged and it won't be able to hold any more charge, and once that happens, current is no longer going to flow, and what you will then have is you'll have this break in your circuit where current can't go through. And so that's what I'm talking about here, is if you have steady state means if you leave the circuit going for a long time, what's going to end up happening at the end of it, that's steady state. And what the saying is, if you have a DC source in steady state, the capacitor is going to become an open circuit. Now, for the last thing here, we have a couple of quick examples of how we can use our relationships between current and voltage in order to figure out for a given capacitor here. So we had this relationship that the current is C times the derivative of the voltage. We have the voltage here as a graph. We want to find the current. So again, it's going to be C, which is 0.02, that's 20 millifarads, times the derivative of the voltage here. Now we're going to go ahead and assume that the time is in seconds, and then this 50 is in volts. And you really would need to know exactly what those units are. And so we need to take the derivative. Now, if they give you a formula like in a calculus class, you can take derivative. X squared goes to 2x, things like that. But they don't give you a formula here. Instead, they just give you a graph. In general, finding the derivative based just on a graph can be tough. But when your graph only consists of straight lines, the derivative is just the slope of those lines. So for this first part here, if I take my slope, the change in y is 50, the change in x is 1. So my slope here would be 50 volts per second. If you multiply that times the 20 millifarads, right, C times that, we will get the value of the current there, which is going to be 1. So it starts out where the current is going to be at 1 amp. Then for the next part of the graph, now we're going to have a negative slope. And you can check, it's just going to be exactly the negative 50 here. It's going down at the same rate it was going up before. So for the same calculation, we're now going to be at negative 1 amp. That's from 1 to 3. Then from 3 to 4, it goes positive slope here of 50 again, which means it's going to go to positive 1 as you multiply by C. And after 4, it has a slope of 0, so you're going to have 0 current there. And so this would be our graph of current in this particular case. Notice that the current can jump around. The current won't necessarily be continuous for a capacitor, but the voltage will. On the other hand, in the second example here, we're flipping it around. And this time, instead of saying that we have a voltage to start, we're saying we have a current to start here. So this is going to be in amps, and T will again be in seconds here. So this time, instead of taking the derivative of our graph, we're going to be taking the integral up here, which is going to be harder. So what I'm going to do is I'm going to go ahead and try to write this current out as an actual function. So in the first part, from 0 to 1, it's a straight line with a y-intercept of 0 and a slope of 50. So that'd be 50t. T goes from 0 to 1. On the second part, from 1 to 3, it has a slope of negative 50. And we'd also need to know what the y-intercept is. If you continue it back, you'd have a y-intercept of 100. So negative 50t plus 100 from 1 to 3. And lastly here, from 3 to 4, it's going to be a positive slope of 50. And then the y-intercept here, I guess it's actually going to be negative. So let's see here. It's already negative 50, negative 100 going down, negative 150, negative 200 here. And you can always double check that the numbers match up by plugging in, say, t equals 3 and see that you get the same answer of negative 50 in each case. Okay, so once we have that, we can go ahead and integrate things. So again, v of t is basically 1 over c times the integral of I of t. So we are going to be dividing by the capacitance time. So we have to divide by the 0.02. So that's going to work out to be 2500 t squared plus some constant. All right, so I'm just integrating. Sorry, I messed up there. It's half of that, because the integral of t is t squared over 2. So we have to divide this by 2 here. So we're going to get the 1250 t squared. And then similar things here, we're going to have negative 1250 t squared plus 2500 t plus some other constant. is from 1 to 3. And then from 3 to 4, we're going to have 1250 t squared minus 5000 t plus a different constant here. And in fact, we have to actually care about this last part, because this last part, it might not be 0, because we're integrating 0 means we're going to get some number there. We don't know what it is. So to figure out what these C1, C2, C3, C4 are, we're going to use the values we have. We know that the initial value is 3. And if you plug in 0 into the first formula here, it's going to be something t squared, so 0 plus C1. So that means this first part is going to be plus 3 there. So we can try to graph that. We know it starts out at 3 and it's going to go up. So you put 3 and it's going to be up as a parabola. Something like this. And we can go ahead and check here. We can say, okay, what is the actual value at 1? So if I do that, 1250 plus 3 is going to be up at 1253 here. As you can see, the scales on my axis are not particularly great, but that's okay. Really, most of the time you're just going to be asked to write these formulas down. The graph is just trying to help us understand what's going on here. Now, to figure out the other constants, we have to know that the voltage function is going to be continuous. So that means that the second formula better have the same value, 1253 here. And if you go ahead and plug it in there, you're going to have negative 1250 plus 2500 plus C3. So V of 1 is supposed to be 1253, but it's also negative 1250 plus 2500 plus C2. Again, just using this one right here now. And so that gives me a C2 that is also 3. Continuing on, so it's going to be a parabola going downwards here. And down until we get to 3. Now let's figure out what the value of 3 is here. So the value of 3 is going to be negative 1250 times 3 squared plus 2500 times 3. And our C2 was 3. We worked that out. So let's do some quick calculations here. And what are we going to get? Looks like some really far down here, negative 3747. And then we want to see what happens if we try to get that same value in the fourth line here. So that would be 1250 3 squared minus 5000 times 3 plus C3 is supposed to equal the same number. And we go ahead and do some calculations here. Plus 5000 times 3. And I'm getting a C3 of 3 here, it looks like. And it's going to continue up here. And the last thing we need to figure out is what's going to happen at the value of 4. And if we go ahead and plug 4 into this, into the final formula there, we're going to get a value of 3. And since the current is not going to be changing anymore, it's always going to be 0 at that point. That means the voltage is going to stay constant now at 3. Now again, the graph is far from perfect here, but what I'm really going to be looking for is seeing that we can write out this formula here and finding your constants. As you can see, it's quite a bit of work